Okay, in this section I'm going to introduce matrices, and we'll talk about how you can use matrices to solve systems. So what is a matrix? Well, a matrix is just a rectangular array of values. The size of a matrix is represented by its number of rows and its number of columns. This matrix is a 2 by 3 matrix because it has 2 rows and then it has 3 columns. 1, 2, 3. So we would say that that is a 2 by 3 matrix. Sorry, there we go. 2 by 3. Alright, this matrix is a square matrix and it has 3 rows and 1, 2, 3 columns. And then this is actually called a row matrix because it consists of a single row, and this is called a column matrix because it consists of a single column. Some textbooks will identify the matrices using subscripted letters, and they do that by, like, A11 just means it's the entry that's in the first row, first column. A12 means it's in the first row, second column. A13, first row, third column, and so forth. So I won't talk much about that, but just wanted to give you a heads up that that's what that means when you see the subscripted variables like this. It just identifies the location of the value in the matrix. Now, we are going to use augmented matrices in this section to solve a system. Now, I realize you can solve a system of equations using what I call the cheat key on the calculator, but it's very important in algebra to know how to do something that's called row operations. And by using those shortcuts, you're not going to be able to solve a system you're not going to be able to learn row operations if you just use those shortcuts. And otherwise, and your teacher probably won't let you get away with it anyway. So let's talk about an augmented matrix. So let me just show you what an augmented matrix is. Let's say I have a system like this where I have all of the variables on the left and the constants on the right. So here the coefficient of x is 2, the coefficient of y is 1, and here the coefficient of x is 1, the coefficient of y is 3. So what I can do is I can take the coefficient matrix 2, 1, 1, 3, and then I can augment it with the constant matrix for 8 and 9. So I can put those together and I get what's called an augmented matrix. So on the left of this vertical line you're going to have the coefficients of your x and y values, and then on the right you're just going to have the constants. So it's pretty easy to once you have a system that's written in this form, and of course make sure it's written in this form with all the variables on the left and the constants on the right. And so here the coefficients are 1, 2, negative 1. So over here we have 1, 2, negative 1. The second row coefficients are 2, negative 1, 1. So over here I have 2, negative 1, 1. And here it's 1, 3, negative 2. So I have 1, 3, negative 2. And then the constants are 1, 6, and negative 1, and they go to the right of the vertical line. Now, I usually write a solid vertical line because it's quicker, but some can use a dotted or dashed vertical line. You could actually avoid the vertical line altogether, but the problem is you wouldn't know whether you're dealing with augmented matrix or a non-augmented matrix. So I prefer to put the vertical line. Okay. So let's talk about some legal row operations for matrices. Well, with a matrix, with an augmented matrix, I meant to say. So with an augmented matrix, number 1 says any 2 rows may be interchanged. Now what this means is that whatever the solution is to the system, swapping rows will not change the solution. So if I had this system 2x plus y equals 8 and y plus 3x equals 9. If I swap these 2 rows then and put the bottom row at the top and the top row at the bottom, it's not going to change the system. we learned earlier that the answer to this was 3, 2. So we're kind of cheating here because I'm telling you the answer is 3, 2, and I'm telling you that the answer is going to be 3, 2 regardless of whether it's in this form or whether it's in this form. Okay, now the second one says I can multiply a row by a non-zero constant. So if I wanted to multiply, let's say for some reason I wanted to multiply row 1 by 3. So let's say I multiply row 1 by 3 and I put the result in row 1. So I'm just going to replace row 1 with 3 times row 1. Well, if I do that, 3 times 2 is 6, 3 times 1 is 3, 3 times 8 is 24. Okay, well, I'm telling you it's not going to change the solution. The solution is still going to be 3, 2. I mean, you can check it. Actually, 6 times 3 plus 3 times 2 will equal 24. And so the answer is not going to change. And then the last one, this is a little more complicated. You can take a multiple of one row and add it to another row. So let's say I wanted to multiply row 1 by 3. Now I'm not going to change row 1. I'm just going to multiply it by 3. So let's say I multiplied it by 3, so that would give me 6, 3, and 24. And then let's say I wanted to add that to row 2. Well, if I add that to row 2, then 6 plus 1 would be 7. And I'm going to put the result in row 2. 3 plus 3 would be 6, and 24 plus 9 would be 33. Now, those 3 row operations, I just kind of did them randomly to show you that you could do these row operations. But actually, our goal is to do these row operations in a certain order so that we can get our matrix, our augmented matrix, in a certain form. So let's talk about that form that we want it to be in. Now, since I already know the answer to this problem, let me just show you what our goal is. Our goal is to take this augmented matrix that we start with and get it into this form here. Okay, because once I get it in this form, then I could take it out of matrix form and put it back in equation form, and this would read 1x plus 0y equals 3, which is equivalent to saying x equals 3. And the second row would read 0x plus 1y equals 2, which is equivalent to saying y equals 2. Similarly, if I could take this matrix and write it like this, then the first row would tell me that x is 2, the second row would tell me that y is 3, and the third row would tell me that z is 1. Now these two matrices have they have a special name. They're actually said to be in reduced row echelon form. So that's right here, reduced row echelon form, or RREF. So once we get an augmented matrix in that form, we can identify the solution or solutions, or we can determine if it has no solution. So for a matrix to be in that form, there are some rules you can follow, but if you just follow my advice, we'll be able to get there. But any row of all zeros must be in the last row. The first non-zero element in each row must be a leading 1. So notice here, each of these first elements in the rows are 1s. Okay, all other elements above or below the leading 1 are 0. So here's a leading 1. Notice everything up below it is 0. Here's a leading 1. Everything above it and below it is 0. And here's a leading 1. Everything above it is 0. And then a leading 1 below a row must be to the left. I'm sorry, it should be to the right. My bad. To the right. So that should be to the right. So this one should be to the right of that one. This one should be to the right of that one. Okay. So that's the 4 things that must be followed. Here's a few examples. Now, sometimes you'll get a solution, a unique solution like here, like in these first 2 cases. But in other cases, you may not get a unique solution, because this one would be an example of a dependent system. And so would this one. This would be an example of a dependent system. And actually this one would too. Now remember, if you ever get a matrix that has a row with all zeros and a constant, well, that tells you that you have no solution. Because, for example, if this had been a 0, then this row would say 0 equals 4. And since that can't be possible, we would know that system has no solution. So how do we get there? How do we get to reduced row echelon form? Well, the first thing you want to do is get a 1 in the first row and the first column entry. And you can do that by swapping rows, or you can multiply the first row by a constant. And then after we get the 1, we multiply that row by a constant and add it to any other rows to cancel all elements that are above or below the 1. And then we move on to the next row and do the same thing. So it's not too bad with a small system. I always start students out with small systems because it's much easier to follow. So let's say we started with this system, and you saw that we can put it as an augmented matrix like this. Now, what I'm going to do is I'm going to just swap row 1 with row 2. That way I'll have a 1 in the first row, first column entry. Now, I'm copying from above each time here, so I'm actually doing more steps than are necessary, but I think it's easier for you to see if I do it this way. So now here's the matrix that I got from above, and I've got this 1, and now I want to make this 2 go away. So since this is a 1, if I can figure out what to multiply this by so that when I add it to 2 to cancel it, then that 2 will become a 0. Well, I know if I add -2 to 2, that'll give me a 0 here. So I'm going to multiply row 1 by -2. Now I'm not really going to change row 1. Well, I'm actually not going to change row 1. I'm just going to do this in my head or on scratch paper. So -2 times row 1. Well, let's see what that would be. Let me write up here what you would get if you multiplied everything by -2. So up here in the red, you'll see that if you multiply row 1 by -2, you'll get -2, -6, -18. And we're going to add that to row 2. So -2 plus 2 is going to give me 0. And then -6 plus 1 is going to give me -5. And -18 plus 8 is going to give me -10. So that takes care of that row. So I've completed what I call the first pivot. Now I went ahead and copied that matrix down here for you. And now once we get the 1 and the zeros in this column, we want to go to the next row, and we want to make this guy be a 1. Well, in matrix speak, we don't say divide. We multiply the row by the reciprocal of -5. So we can just multiply this row by the reciprocal of -5, which is -1/5. And we'll put the result in the same row. So 0 times -1/5 is 0, -5 times -1/5 is 1, and -10 times -1/5 is 2. So now we have a 1 here, and the next step is to figure out a way to get rid of the 3 that's up here. So here you can see that I've copied down the matrix again from the step above, and I want to eliminate this 3. So I can use this 1 here by multiplying this 1 by -3. So if I multiply by -3 and add it to row 1, that'll cancel the 3. So if I multiply everything in this row by -3, I'm going to get 0. 1 times -3 is -3. 2 times -3 is -6. And now I will add these to row 1. 0 plus 1 is 1. -3 plus 3 is 0. And -6 plus 9 is 3. And now I have it in reduced row echelon form, and I can easily read the answer. X is 3 and y equals 2. And that's how we solve it. Okay, let me finish up by just kind of summarizing this second one here. You see I wrote it in augmented matrix form. I wanted this to be a 1, so I multiplied row 1 by 1/3, and so that changed these values. Then I want to use this 1 to eliminate the 4. So I'm going to multiply everything in row 1 by -4 and add it to row 2. And when I did that, I got this for my new row in row 2. And then after that, I want that 7/3 to be a 1, so I need to multiply that by 3/7. And when I did that, it gave me this row, 0, 1, 3. And then after I did that, I wanted to multiply this row by -2/3 and add it to row 1 to cancel the 2/3. And then I get the answer, x equals -1 and y equals 3. And so that's your answer. And I will work some more for you in the next video.